So in this next lesson, we're going to take a look at what's called composite transformations. Now, if that sounds like something we've already talked about, it's because we've talked about both of these topics separately. We've talked about what it means to be a composite function, okay, and that's where you basically take one function and apply it to another. And we've done a whole lot of work with transformations in this chapter. What we're going to do now is we're going to do composites using transformations. So we're going to apply one transformation on top of another. So we've talked about two types of transformations, scale changes and translations. And so basically what we're going to do is we're going to treat it like a composite function where we're applying the translation and then we're applying the scale change on top of that. So if you look at this first example, I'm giving you a scale change rule and a translation rule. Those should look really familiar from earlier in this chapter. And it says write an equation for f of x under the composite s of t. So thinking about what we know about composite functions, the t needs to be applied first, right? So I'm going to start by just writing the just writing the translation rule, and then we'll go in and apply the scale change on top of that. I'm digging for a different color here. So if I'm just applying the translation rule here, I know that I want to take my y, which is really my f of x, and subtract 5. So I'm going to say y minus 5 equals, and then for my x, I want to do x plus 1, but I'm going to put that in parentheses with the x before I square it. So I'm going to make this x plus 1 squared. Now, the thing about composite transformations is when I go to apply the second part of this, when I go to apply the scale change, I'm applying it not just to the y, but to the y minus 5. I'm applying the x part to the x plus 1. I still want to make sure it's happening before I square, but I want to set it up so the x plus 1 is happening first. So when I see 3x, that would normally tell me to divide by 3. I am still going to divide by 3, but I'm not just dividing the x by 3, I'm dividing this entire thing by 3. Still inside the parentheses here. And then for the y, it says to multiply by 2. I don't want to just multiply the y by 2, though. I want to multiply this whole thing by 2, and the easiest way to do that is with parentheses. So this right here, would be a perfectly fine answer for me. You could leave your answer just like this, and in fact, that's probably what I'm going to do when we take a look at it in Desmos. If I did want to clean it up some, there's not much I can do here. I could write that divided by 3 as a 1/3 in front, but I actually think it looks cleaner this way. But I could divide by 2 to get the 2 over on this side. So that would give me y equals, I'll deal with the 5 in a second. I haven't talked about that yet, but x plus 1 divided by 3 with a 1/2 in front of it because I divided by this 2, okay? And then the minus 5 could also be moved to the other side as a plus 5. Oh, and I forgot my square here. Sorry, messing that up all over the place. So if I did want to move it all to this side, this is what this would look like, okay? And again, there are some ways that I could clean up this squaring, but I think this is the cleanest way we can write that. What I do want you to notice is that these numbers that came from the y side are outside of these parentheses, so that's how I would identify that they belong to the y. I also want to point out that they're exactly the same as what I saw in my transformation rules. So 1/2 y divided by 2 plus 5 plus 5. They don't have that flipping thing going on. They don't have that reverse sign or anything like that. And that's just because we had to flip them again when we moved them to the other side. So the multiplying by 2 became a dividing by 2 and so on. Okay, describe the effects of the transformation. I think you guys can handle this. We've done this a lot. But there's 4 things we have to identify here. So in the 3x, the scale change rule, 3x and then y divided by 2, I would say that this represents a horizontal stretch because we're multiplying by 3. And the y over 2 represents a vertical shrink. Now I want you to think about what that's going to look like on a parabola, right? If we have a parabola that looks like this, a horizontal stretch would be like me grabbing the sides of this parabola and pulling it outward. So I'm expecting it to get wider. And also a vertical shrink means I'm coming up on top of this and like pushing it downward, which is also going to make it appear wider. So both of these things together are going to make this parabola appear wider than it was originally. And we're going to see that in Desmos here in just a second. And it's going to be hard to tell like what's causing what. But essentially these two transformations are working together to make that parabola look really wide. And then we also have to talk about the translation. So x minus 1, y plus 5. These are slides, right? Translation. So x minus 1, that's moving us 1 to the left. And the plus 5 is moving us 5 up. Okay, I do want to hop over to Desmos and show this to you. So let's start with just y equals x squared. And I'm going to take that and I'm going to make it a black dotted line. Might also make it a little bolder so you can see it. So there's my original y equals x squared. I'm going to graph the equation that I had here in pink before I put the 2 and the 3 in here. So before I added the translation, before I added the scale change, when I just had the translation, this is what our graph looked like. Y minus 5 equals x plus 1 squared. Okay. I'm going to make this brighter just because on the video screen I want to make sure you can see it. And so these two parabolas are exactly the same, but the red one is shifted 1 to the left and up 5. Okay, that's where my new vertex is, so we can see that that shift occurred. Okay. So now let's add in the 2. So I'm going to wrap this in parentheses and I'm going to multiply by 2. And if you were watching there, the effect that 2 had is it pushed the top of the parabola down, which actually made it spread out a little further left and right. It took all of these points on the parabola and pulled them downward, which is going to make it grow more slowly. Okay. The next thing is we had the x plus 1 and we divided that by 3. And now we have a really wide parabola. That one's even wider because the 3 is also being squared, so makes the effect even larger there. But you should see that we have a parabola that has still been shifted. Where's that? I can't tell. Yeah, there's my vertex. Sorry, I didn't mean to click on that point. The vertex has still been shifted from 0, 0 to negative 1, 5. So we're still seeing that translation occurring here, but we also have the scale change that made the parabola appear wider. Okay, and so that's what these composite transformations are all about, is doing one and then the other. Now you'll notice that I did the translation first here, and technically in the directions the way this was written, that's why I did that, is because it says to do the translation first. But we usually do the translation first, and the reason for that is we technically are supposed to follow order of operations when we do these transformations. So like this rule is multiplying and dividing. This should actually be happening before this happens. But remember how the equations, everything works backwards? That works the same way with your translations and your scale changes. So we usually would follow order of operations, but we do it in reverse when we're putting it into the equation because, again, the equation is backwards land. Okay? Okay, example 2. So this time I've given you a big verbal description of a whole bunch of things. These 3 things should all be covered by a scale change, and these 2 things should all be covered by a translation. If you want to pause the video and get ahead of me a little bit, you're welcome to. But we're going to write a rule here. So let's say our scale change is, we want a horizontal shrink by 3. So that's x divided by 3. A vertical stretch and a vertical flip. So we're going to multiply by 5 and also make it negative. Okay. That's going to give me a vertical stretch and vertical flip. And then we're going to do a translation right by 2. So that would be x plus 2. And down by 6, y minus 6. Okay, and then it says, let's go ahead and put this on your favorite parent function, and then we're going to verify it by graphing it. So you pick any parent function you want. If you want to do something different than me, that's great. but I would love for you to hop into Desmos too and check yours out and make sure it actually works. I'm going to do, just because I think it'll be easy to see what's happening, I'm going to do the square root function. Okay, so this is my parent function that I'm working with, is square root of x. So first thing I'm going to do is apply the translation rule, the pluses and minuses. So I'm going to make it y plus 6 equals the square root of x minus 2. So that would accomplish my translations, right? And then I'm going to go in with my scale changes. So this is going to make me multiply the x by 3 and divide the y by negative 5. So I'm going to have y plus 6 divided by negative 5 equals square root of, now remember, I want to multiply all of this by 3. So to accomplish that, I'm going to put this in parentheses, but notice it's still inside the square root symbol, because I want to apply it to the x before the square root is happening. So all of your transformations need to happen to the x inside of the square root symbol. Okay, let's see if we were correct. So now I want to make this graph the square root of x. And my transformed function, so once again, I'm going to start with just my translation, just so we can see it by itself. So y plus 6 equals square root of x minus 2. And so you should see, it's probably not going to let me click right on the endpoint. Oh, maybe it will. I don't think it'll stay there. But this shifted to the right 2 and down 6. Okay, and that's what we wanted, right? To the right 2 and down 6 from my original point of 0, 0 here. Okay. And then we applied our scale change. So we are going to take this whole thing and divide it by negative 5. So right there, I can see that this thing flipped over, right? And it's a vertical stretch, okay? So it got taller. I mean, taller in reverse because it's going in a negative direction now. But it's a taller arc than it was before. And then I'm going to take this and wrap it in parentheses before I multiply by 3, okay? And that, again, made it seem taller. Let's see if I can zoom this out some. Because what was really happening is I was grabbing points from over here and dragging them inward, okay? So let me take that 3 back out of there for a quick second. If I took, let's say, this point right here, okay? I just picked a point randomly, and I dragged it, I don't want to drag along the function, but I dragged it straight horizontally to, like, let's say right here. I mean, technically what I should have done with it is divided it by 3. But if I took this distance and I pulled it inward, you can see that that's going to make the arc of your curve taller, okay? And so that's what you're seeing here, is you're seeing both a vertical stretching, so you're seeing all the points being pulled downward, and a horizontal shrinking. You're seeing all of the points be pulled towards like the center of the graph, okay? So check, we accomplished all of these things. We're in good shape. Okay, one quick thing I want to say about this. I told you that I was perfectly happy with you leaving your equation like this. I actually like this form of the equation best because I can see all of the things that are happening individually. But some mathematicians are grossed out by all those parentheses and all of that, you know, the y not being by itself and all of that. And so they come along and they meddle. They take our equations that are all set up the way we like them and they clean them up for us. And then we get something that looks like this down here. So notice that this example, you've got y all by itself. So you've got some numbers over here that actually belong with the y. And look specifically, excuse me, at what's happening with the x. We see that it's been multiplied by 2, but this number looks like it should be a 6, and the problem is it's not. We multiplied it by 2 and distributed, and so this 6 is not really a 6. This 6 is not really a translation of 6, I guess I should say. It really is a 6. But so we need to rewrite this thing in this form. I want to show you real quick what this equation would look like if I cleaned it up like this one. So I could distribute here and make this a square root of 3x minus 6. I could also multiply by the negative 5, so I could have a negative 5 sitting out here. And then I would have a plus 6 left over here, so I'm going to put a minus 6 on the outside here. And then this y would be all by itself. That's the simplified version of this. You have to be able to look at this and recognize two things. First of all, this -5 and this -6 don't belong with the x. These both belong to the y, and I know that because they're not inside the square root symbol with the x. Okay, so I have to recognize that those two are y transformations, not x transformations. The other issue is here. I can look at this and say, well, I know the x has been multiplied by 3, but that means my translation number also got multiplied by 3. So I really need to put it back in this. This is called factored form. I need the 3 separate from the x. And we did a little bit of this when we did completing the square. So this part shouldn't be too crazy difficult for you. So when I am looking at this function, well, first of all, what is the parent function? We can answer that. Y equals the absolute value of x. When you get a question like this one where it says to describe the transformation in words, I can't emphasize this enough. You want to be looking at the rules, not the equation. So even if it doesn't specifically say, hey, write me the rules for this transformation, we really need to do that before we can describe this in words. And in order to find the rules, I need to clean this thing back up, right? So the very first thing I'm going to do is take this 2x minus 6 and I'm going to factor out a 2. So I'm going to make this 2 with parentheses, x minus, and then if I pulled that 2 out, this 6 is really a 3 in disguise. Okay, I want to write it this way so that I can see the scale change separate from the translation. Also, I want to recognize that this 3 really belongs over with the y, and this 4 really belongs over with the y. So if I move the 4 back over with the y, this would be a y minus 4. And if I move the 3 back over, this thing would be multiplied by 3. Okay. Now, I'm totally fine with you writing these over here, but when we're writing our rules, we want to be able to look at it this way. So we've got this going on with the y, we've got this going on with the x. So now for our rules, our scale change rule, that's my multiplying and dividing, is, let's see, I'm seeing, well, let's start with x. X is being multiplied by 2. So in my rule, x is being divided by 2. And y is being multiplied by 3. So in my rule, y is being divided by 3. For my translation, I can say x is being shifted. Well, my rule should be x plus 3, right? We'll talk about the shifting here in a second. And my y should be plus 4. If you don't rewrite it this way, you're going to get this number wrong. Okay, so it's really important that you know to factor that 2 out before you write your rules. And now I could hop in here and I could say, you know, this is a horizontal shrink by a factor of 2. This is a vertical shrink by a factor of 3. This is a shift to the right by 3 and a shift up 4. Okay. One more time with Desmos here. We said our parent function was absolute value of x, so here's that, absolute value of x, okay? Get it nice and centered. The equation they gave us was, the original equation they gave us was y equals absolute value of 2x minus 6 divided by, sorry, I lost my place on my paper. Well, actually, let's just talk about this for a second, 2x minus 6. What you should notice, because all I've done so far are the x transformations, this did shift to the right, which we said it was going to do, but it shifted to the right by 3 and not by 6, right? And so that's why it's important for you to like factor out that 2, because the shift was actually only by a factor of 3. And then it also got twice as skinny. It's a horizontal shrinking. So what we did is we grabbed, for example, this point here, which is -2, 2, and I cut it in half. I cut the x value in half. So it would have been pulled into -1, 2. So it would have put a point right here. And then, of course, that point got shifted over by 3, which made it show up over here. I don't know exactly where, but it's there somewhere. Okay, back to what we were doing. This was all divided by 3. Okay, notice that stretched it back out again because what that did was a vertical shrink, which pushed everything back down. And then a +4, which we're expecting to shift it up by 4, which it did. That's where that's at. Okay, so you can notice that new vertex is at 3, 4, and that's because of this shifting right here, the right 3 and up 4. Okay, that's about it for today. Really, it's not a whole lot that's new. It's just doing 2 things at the same time. The biggest new thing is understanding to do this with those composites. So that's going to be really critical for you moving forward. But other than that, give this a try. We'll practice and review it in class like usual.